Hello and welcome to our final project presentation. My name is Cameron Carpenter, and this project I worked with Jordan Richardson and Gary Swiney. In this project, we aim to implement a robust machine learning pipeline to pre-process, analyze, and classify a complex dataset. So our goal was to evaluate the performance of various classifiers under different pre-processing configurations, including normalization, feature selection, and dimensionality reduction. We also explored the use of clustering techniques to gain deeper insights into the data. So the project requirements emphasized the following. So we had our pre-processing, applying normalization methods like standard scalar and the min-max scalar to ensure all features were on the same scale. Then we had our feature selection using techniques such as variance threshold, RFE, and select k-best to ensure model performance by removing irrelevant or redundant features. And then we also had dimensionality reduction. So here we're leveraging PCA to simplify the dataset and improve interpretability while also retaining the most important information. And then we had our classification, testing a variety of classifiers including SVM, random forest, gradient boosted trees, logistic regression, KNN, and ensemble methods like ADA, boost, and bagging. And then our evaluation, using metrics like F1 score, AUC, and silhouette scores to evaluate model performance and clustering quality. So for this project, we decided to focus on SVM as our primary classifier because it consistently delivered the best performance across all metrics. We also evaluated other models like our gradient boosted trees and the random forest, which performed well but did not surpass SVM ultimately. In addition, we incorporated clustering techniques like k-means and agglomerative clustering to analyze the grouping of data points and also validate our pre-processing and classification steps. So throughout this process, we adhere to the best practices by using pipelines and grid search for hyperparameter tuning, ensuring modularity and scalability. So our results demonstrate the effectiveness of this approach, and we are excited to kind of walk you through the details in the rest of this presentation, as well as our results.
Hello, my name is Gary Swiney, and I am reviewing some of our results for our final project. So, first we'll start with figure E1. Here is our best model's performance against our Kaggle data, and we used a test train split, 20%, in order to achieve these numbers. We get a test accuracy of around 9055, which is pretty good, and we see it's achieved with SVM and PCA component 7, standardization, normalization, and variance threshold feature selection. Some things that aren't noted here are the hyperparameters. We use a grid search right here in our code in order to go through our hyperparameters for SVM and capture the best one. So that was our best performance that we recorded on the day. Here is our clustering. This was achieved again with 7 PCA components, variance threshold, standardization. So that is found standardization, variance threshold, PCA 7 right here, model number 1. As you can see here, there's lots of overlap in the clustering that will result in a high silhouette or a low silhouette score, because some of these predictions will be far away from closer to the center of other predictions than they are their own cluster due to the large amount of overlapping. If we saw a higher silhouette score, we'd see less overlapping, but overlapping is to be expected once we start looking at some of our samples and how muggy the data looks. Here's our confusion matrix. As you can see, it aligns with the 90.5% accurate-ish, as you could tell. Lots of correctness along our diagonal with, some misrepresented ones around the edges. It looks like most are around bike. Bike was the most misclassified. In figure E4, we can see some of our top correct samples that we got right. These are pretty clear pictures. Some of them are. Some of them really aren't. Like this one, you would think it would be person, but it's not. It's looking at the thing behind the person. Stuff like that. And here are some of the top incorrect samples. Some of these are pretty messy, as you can see here, but this one, this one of a bike right here is, to us, we could tell pretty clearly what it is, at least a shadow of it. In figure E6 through E10, we begin to see the performance of some of our other models. And this is just to show that we analyzed a lot of different classifiers before settling on the one we did. So we see logistic regression here, performing okay, a little bit worse. Random forest performing pretty good, but not as good. KNN, variance threshold, ADA boosting, and bagging, all performing just a little worse than SVM. So really establishing that SVM was performing the best, even though some of these have higher silhouette scores. And that concludes our analysis, but in the report. It's good to say that we do generate our sample submission CSV, which is to be submitted along with this assignment, along with our 30 predictions on the data. And in order to generate our scores, test train was necessary because the instructor does not supply the correct labels with the testing data set to make predictions on, because that it could someone could just cheat and have all the answers immediately. But that concludes our analysis of the results. Thank you.
Hello, my name is Jordan Richardson, and this is the CSE 546 Introduction to Machine Learning final project. And my teammates covered the introduction and most of the results already. So just to kind of go forward with this, the way we split up the task, Cameron Carpenter led the pre-processing phase, dataset merging, normalization methods, and feature selection methods. I worked on the classifiers, integrating the grid search for hyperparameter tuning. I made sure K-fold was working accurately, and then added the accuracy measures. Gary Swiney helped a lot with the code and in debugging and refining it, making sure that our pipelines were set up correctly, checking out the plots, and kind of the analysis side. Working together was actually really good. Some classes I don't have as much luck, but all of the team put in quite a bit of work on this project, so I'm very happy with that. So we completed this project, and I will go over what our final results were. So we were given a final data set. It had 30 test samples, and the key about this was that these samples did not have the image name and a class columns, which means that you don't know what's actually correct, and that's the point, because then we will use our best model that we trained to then predict on these and output that as a sample submission here. And I know that's just numbers, but that was the format we were asked to put this in, to see a more clear idea of kind of what happened. We also created one that printed it out with the titles, or the labels, I should say. I did want to give just a small sample. I know it wasn't requested in the assignment, but we had extra time just recording. The team worked together really well, and we split up the work, so there's quite a bit of time. So I'm running a much smaller pipeline. It's only doing PCA 2, 5, and 7, because some of those were some of our better PCA values. And I have it limited to standardization and variance threshold, because we didn't need to consider any other, because we have already identified basically the best parameters for the classifier SVM. And so this will then classify each of our models based on their test accuracy. So you can see that it goes down. And then because I'm only doing 3 models or 3 PCA components, this is all the graphs you get. But you can see how the silhouette score is much higher for model 1 or model 3. I apologize for that. And model 3 is this one right here. And so if you actually look at the graph, you can tell that there's a lot of overlap between these. And there's still a lot of overlap here. But then when you come over here to 3, where the silhouette score is 0.4438, the overlap is a lot less than these two. So that kind of is what silhouette scores are. It gives you an indication of how your data is clustering. But not necessarily does that mean that that's the best model. After that, we had our confusion matrix. This was covered by one of my teammates, so I won't cover this much. And then we actually had trouble with missing images or image names after importing between both of the extra hard samples and the data.csv that we were provided initially. We had to concatenate those, and as well as adding images in here. And I believe that's what messed up our images as a whole. But we do have those in the report. And then you can see here that it prints out the predictions, and we'll update this file, which it will be the same. That really concludes the project. Well, I think we all learned a lot in this project. There's a lot of different classifiers out there, different machine learning models that work better for different data sets. And we've used quite a few over the class. Some of these models would have worked better for, and some of them worked good on this one. It also taught us a lot about using pipelines and grid search, because this project was on a much larger scale than before. But overall, it's been an excellent opportunity to apply machine learning concepts to a harder data set than what was covered in some of the class. We got to use PCA, hyperparameter tuning, and cross-validation, and really we were able to push ourselves to do the best we could because the teacher incentivized us to do so, which is great. Well, this is Jordan Richardson, and this is the end of our project. Thank you.